Okay, this is the theory of chapter 7. We already did two important examples or two videos already about the main ideas of this chapter. And as I said before, this chapter is the most important chapter of the statistics, and because this is the key word in any class in statistics, which is the sampling distributions. And why this is important? Let's look at this scenario. A director of tourism country conducted a study that showed that the mean daily expenditure for adult visitors to the country is $318. The mean value is based on statistical sample of 780 visitors. So this number is based on a sample. They took a sample of 780. They found that 318 is the average daily expenditure for these visitors. So because this is the mean of the sample, it's a statistic, it's not a parameter. Okay, it's a statistics. Because it's based on a sample rather than the entire population, it's a statistics, not parameter. If you were this official, you might have some questions. And these are important questions and valid questions to be asked. Is their actual population mean equal to 318? Is it really going to be equal to the population mean? If the population mean is not 318, how close is it? How this number close to that true population? Is this sample 780 is taken from a population of almost 2 million annual visitors to the country sufficient to provide a good estimate of the population mean? So all of these questions are valid, and yes, we care. We need to know about these things. So that's why we took a sample, and we would like to make a decision about the population. And as I said before, we crossed the bridge, chapter 4, 5, and 6, and chapter 7 starts telling you some stories about the population. So now we'll be talking about the sampling error, as we said in the previous videos, and the sampling distributions, right? And as we said, this is the building block to understanding the statistical estimation and hypothesis testing. Sampling error, as we did in that video, is the x bar minus mu. X bar is the sample mean, mu is the population mean. We did all of these already. So if you did not watch the first two videos, you have to watch them so you understand what did we find. And we comment on these findings already. And we did the mutual funds example as well. And this is theorem 1 that I told you about. For any population, the average value of all possible sample means, all possible sample means computed from all possible random samples. The word all is key word. Of a given size from the population equals to the population mean. That's exactly what we said. Do you remember when I said the average of the averages? This is the average of the averages. This is the average of the averages. This is the average of the sampling distribution. And the mu is the population distribution, okay? So when the average of all possible values of the sample statistics equal to the corresponding parameter, which is in this case, we're talking about the mean, the population mean. We're talking about the mean of the sampling distribution. So we call this unbiased estimator. In this scenario, we talk about the parameter. This parameter is the mean, okay? We'll be talking about as well the proportion. So this is valid not just for the mean, it's valid for the proportion as well, the population proportion, okay? Theorem number 2. Do you remember when we talked about the sampling standard deviation? For any population, the standard deviation of the possible sample means computed from all possible random sample of size n is equal to the population standard deviation divided by the square root of the sample size. So the standard deviation of the sampling distribution, standard deviation. So that's why we call it sigma sub x bar, because we are finding the standard deviation of these values. Do you remember these x bars? It's the standard deviation of the population divided by square root of n. Theorem 3, it's an example of the mutual fund. The mutual fund, the population was not normally distributed, but if you increase the sample size, the sampling distribution is going to be approximately normal. If you actually make it bigger sample size, the 30 was enough, by the way. If the population is normally distributed with mean mu and the standard deviation sigma, the sampling distribution of the sample mean x bar is also normally distributed with a mean equal to the population mean and the standard deviation equal to the standard deviation of the population divided by square root of the sample. And this is consistent estimator. This is consistent estimator, which is unbiased estimator, because the difference between the estimator and the parameter tends to become smaller and smaller and smaller as the sample size becomes larger and larger and larger. These are becoming equal as the sample size increases. These are becomes equal as the sample size increases. And again, watch the video to understand what we are talking about here, the previous video. The video is about the important concepts or important introduction about the sampling distributions. These are a very good example. Look at this population. It's already normally distributed. If you take a sample and you do sampling distribution, it's normally distributed. The sample is 5. Increase the sample, it becomes more nicely, what do you call it? Normally distributed, and actually it's consistent estimator. It's consistent estimator, right? As the sample size increases, we still have normally distributed curve sampling distribution. Now the idea is what? The idea, if you remember that we talked about, if you have an x value, every x value has a standardized value z, right? How do we standardize the value z? We look at the z, we look at the population distribution, and we said, okay, x minus mu divided by sigma, because we're talking about the what? We're talking about the population distribution, x minus mu divided by sigma. But now we can standardize x bar, because we don't have now population distribution, we have sampling distribution. Now we are talking about sampling distribution here, and the values in the x-axis, do you remember that the values in the x-axis are x bar, not x? So we want to standardize x bar, not x. So we want to standardize them to z. What does this equal? Equals to the z equals x bar is the value on the x-axis minus the mu of x bar, the average of these values, divided by the sigma x bar. This is, look, again, this is population mean. This is, sorry, the population distribution. What is the population distribution? It's this. Here we're going to have the mean of the population and the standard deviation of the population. If I give you any x value somewhere here, this is x, suppose that this is x, and I ask you to standardize this value, what you do this. But if I give you sampling distribution, the sampling distribution is going to look like this. Here is going to be the mean of the samples, mu x bar. And the standard deviation is going to be standard deviation of the samples. And these values here, they're going to be x bars. If you remember, a mutual fund, go to the mutual fund. And I ask you to standardize this. How do you standardize that one? Using this formula. Using that one. And from previous theorem, we said that, okay, x bar, but we know that mu x bar is equal to the population mean. There's no need to worry about this one because we know it. Because if you take all the samples, the mu x bar is going to be equal to mu. Go back to theorem 1 or 2. Also, the standard deviation of the sampling distribution, which is, we call it standard error, by the way, it's sigma divided by radical n, or square root of n, right? The last point here is what? Sometimes we need to adjust the z value if you have a finite population. We call it for the correction. There's a correction factor. We just multiply by this correction factor. Finite population correction factor. This exactly occurs when you select large relative sample compared to the size of the population. If it's greater than 5% of the population size, you have to multiply by the relative or the correction factor, okay, to get the z value. This is a quick example. This company, they are making flooring materials for the residential and commercial construction industry. One item they make is a mosaic tile for bathrooms and showers. When the production process is operating according to specifications, the diagonal dimension of a tile used for decorative purposes is normally distributed. So the population is normally distributed. The mean, so this is the mu. So mu is 1.5, and the standard deviation, sigma, is 0.05. Before shipping a large batch of these tiles, the company or the manager or the analysts select a random sample of 8 tiles with the following diameters. So he selected this random sample, and he would like to know the measurements to determine if the process is no longer operating within the specifications or no. Now, this is the idea. Now we are starting making some sense of what we studied so far. Why? Because this big industry or this big, company, they're making kind of tiles, and we cannot test all of these tiles. So you have to take samples now. But we have some ideas about the population mean and the standard deviation, or at least these measurements, they're going to be our standard measures, or these are our target means, and these are our target standard deviation of the population. So we need to take sample and see how it goes, right? But the idea is one sample is not enough. That's why we're going to use the sampling distribution idea. So he took one sample, and after taking one sample, he found x bar. X bar is 1.5. Just find the average of these guys. Now, if you find the average of this sample, you'll get 1.565, right? After that, the question gives you a really priceless piece of information. Says the population is normally distributed, and we took only one sample. But because of theorem 1 and 2, theorem 3 basically, theorem 3, if the population is normally distributed, then the mean of this sampling distribution is equal to the mean of the population. So I don't need to worry about taking so many samples. My idea, someone's going to tell me, why don't we take so many samples and create sampling distribution? No, there's no need to do this, because we already seen that if you have the population is normally distributed, and the example tells you this, then the mu x bar is equal to mu. So the sampling distribution mean is equal to the population's mean. Okay, why do we need to worry about this? Again, also the standard deviation of the sampling distribution is equal to the standard deviation of the population divided by square root of the sample size, right? Which is in this case 8. So if you calculate all of these, if you have, now we have the sampling. Okay, why do we care about this? Yeah, because the goal is, now we are trying to make now connections. Because we would like to know whether, what is the probability, now we're going back to like chapter 6, whether x bar, is it really greater than this amount or no? We're going to study this. Is it out of adjustment or no? So we took only one sample, and we found that the average of that sample is this number, 1.565, and we would like to find out the probability of x bar. Is it really greater than or equal to that number that we found? If we take any other sample, is it going to be greater than this number or no? We have only one sample, so we need to know what is the probability that if you take any other sample, what is the chance that you will be having something greater than this? Because our target mean or our standard is 1.5 inches, by the way, right? So that's why we want to check whether we are greater than this number or no. So to study that part, to study this, we have to standardize x bar to the z, because in Excel or our formulas help you to find the area under the curve when you have z. In the past we had x, now we can use z as well. Or you can actually use the norm dist, by the way, but we have to be careful now. So how to do this in Excel? This is from chapter, now we go back to chapter 6. Chapter 6 says, if you'd like to find the area, now we are studying the sampling distribution, not the population distribution. This is the sampling distribution. This is my mu x bar, which is already, we know it, 1.5. Now we have 1.565 is the x bar. This is my x bar somewhere here. And the question is, what is the probability that if you take another sample, it's going to be greater than this number? What is the probability here? So to do this using Excel again give you the left-hand side. So we're looking for the right, so we do 1 minus norm dot dist. In the past, we used to have x value. Now we don't have x value, we have x bar value. This is x bar value, comma, mu. Mu is a mu x bar, which is equal to the mu, comma, sigma x bar, comma, true. Why 1 minus? Because 1 minus, Excel is going to give you, if you just use norm dist, it's going to give you the area on the left. We need to get the area or the probability on the right, right? So let me get these numbers on Excel and get the answer. So we get almost 0. So this is 1 minus norm dot dist. X bar is what? Is it 1.565, comma. Mu x bar is the same as mu because of theorem 3, 1.5. Sigma x bar is sigma divided by radical square root of n, which is 0.05 divided by square root of 8 sample size, comma, true. What did we get? We got almost 0. Almost 0. What does it mean? It means that this number is just going to be somewhere here, basically, not here, not here. It's going to be somewhere here. So let me delete all of this. So the area on the right-hand side of this is 0. But what is the conclusion? So there's no chance that the random sample of 8 tiles will have a mean of diameter of 1.565. The chance is 0. The chance is 0. Getting a tile greater than or equal to this number is going to be 0 within these specifications. But we took a sample. We have this sample in our hand. We have this, I mean, this sample cannot lie, right? We have a sample and we have the average of this number. So there's something wrong in the process. Because statistically speaking, using the math, there's no chance that we're going to find something has this diameter, 1.565. But actually the process analyst, he already found this sample. So we have a problem. So now we start making connections between sampling distributions and making kind of conclusion, telling something about the population. So we study the sampling distribution now, and we make connections with the population. The next most important theorem in statistics, which is, we call it the central limit theorem. In the previous theorem, theorem 3, there's a specification here. There's an important thing. It says if the population is normally distributed, then this is true. regardless of the size of n. But the central limit theorem tells you much better than the previous one. If you give me any population, this is any population, these are the x values, and you take a big sample, if the sample is big enough, then the sampling distribution is going to be normally distributed. And these are examples. This is the theorem, by the way. For simple random samples of n observations from a population with mean mu, standard deviation sigma, the population's distribution, regardless of the population's distribution, we don't know, skewed, triangle, we don't care. Given that the sample size is sufficiently large, in statistics, large is enough means n is greater than or equal to 30. If n is greater than or equal to 30, then we are good to go. We are good to use this. We can immediately say the sampling mean is equal to the population mean. The sampling standard deviation is equal to the sigma over square root of n, regardless of the population's distribution. But this condition has to be met. Look at this. This is the population distribution. We took a sample of 2. This is the sampling distribution. When we take 5, here we go. Okay, 30 is the minimum that works in all of the cases. That doesn't mean that if we have less than 30, that is not going to be. No, it will be sometime. We don't know. It depends on the data. Look at this population, a triangular. Sampling distribution 5, sampling distribution 30. Look at them, symmetric, symmetric, symmetric. Skewed population distribution. Still skewed, becomes symmetric. Sampling distribution, sampling distribution. Next example. West Side Drive-In. The records, past sales record indicate that the dollar value of lunch orders at the West Side Drive-In are right skewed. So the population is not normally distributed. That's okay. Let's continue. With the population mean, so this is a mu. Let me write this down. $12.5 per customer. And the standard deviation of the population is $5.5. The manager has selected a random sample of 100 lunch receipts. So this is my sample size, which is sufficiently large. This is large. Why large? What does it mean by large? Keep this in your mind. Large means we can use central limit theorem, CLT. What does it mean? Immediately before continuing the question, we can say, okay, the distribution of the sample, the mu, the average is equal to the mu, which is equal to 12.5. And the standard deviation of the sampling distribution is equal to the standard deviation of the population square root of n, which is 5.5 divided by square root of 100, which is 0.55. This is only because we know that n is equal 100. She's interested in determining the probability of what? Oops. The probability that the mean lunch order of this sample from this population will fall between $12.25 and $13. So she cares about what? She cares about knowing the probability P of what? Listen, mean lunch, the mean, so X bar. So she wants to know whether the X bar of this sample from this population, is it going to be between the two values, 12.25, $13 or no? Or she's going to find the probability, not just yes or no. She wants to know the probability that the mean lunch for this sample from this population is within $12.25 and $30, right? And we can use NormDist. We can use two methods. Let me use the two methods here, okay? First method is just using again, how we built this, how we do this. We have to have sampling distribution, not probability, not the population distribution. Sampling distribution is normally distributed for sure because n is large. So this is the sampling distribution. This is the mu. X bar equals 12.5, right? We need to know the probability that X bar is between these two numbers. This is 12.25 and this is 13, something like this. We want to find the probability between these two numbers. This is the goal, to find this region. What is the area of this? And we know that from chapter 6, we can find the area on the left-hand side of the 13 and the area on the left-hand side of the 12.25. But we have to be careful because this is sampling distribution. So it's going to be norm.dist. The area on the left-hand side of the 13 is going to be $13, comma, the mu X bar, which is 12.5, comma, the standard deviation of the sampling distribution, which is 0.55, minus the area on the left-hand side of the 12.25, norm dist of what? 12.25, comma, 12.5, comma, 0.55, comma, true. I forgot the true there, by the way. This is comma, true. Comma, true, this minus. Now, if you do this in Excel, let's see what we get. This gives us 49.3. So it's about 49%. So the chance that this sample mean is going to be between these two numbers is 49%. The other method is what? As we did in chapter 6, we can standardize the X bar. We can standardize the X bar. So the other method, let me use it here. So again, this method, without standardizing, P, we are looking for P, the probability of X bar, the mean, to be between these two values, right? We know that every value can be standardized, so this is going to be between the two standardized values. So X bar will be standardized. How we standardize X bar? So we're going to standardize these two values. How we are going to standardize these two values, we're going to use the Z equals, if you remember, X bar, right? This is sigma over, right? So we're going to standardize this, and we're going to standardize this. So the first one, when X bar is 12.25, then Z equals 12.25 minus 12.5 divided by 0.55. When X bar is $13, the standardized value of the $13 is 13 minus 12.5 divided by 5. Let me get the answer for both. So this is going to be negative 0.45, and this is going to be 0.909. This is 4 here. So either you find, as we said in the beginning, or standardized values for each, and you can look at the standardized normal distribution now. Now, before we looked at this guy, or you can look at this guy with a standard normal distribution. You remember the middle is 0. We are looking for the Z value, or the probability that Z value is located between these two numbers, negative 0.4 somewhere here, and 0.9 somewhere here. So we're looking for this probability. It's the same as the previous one. And how do we find this in Excel? We use norm.s.dist, there on the left-hand side of that guy, which is 0.9, true, minus norm s.dist, negative 0.45, comma, true. Guess what? We're going to get the same answer. The area is going to be about 49%. So the probability is going to be 49%. What does this tell you? And this is really nice, because we are talking about now sampling distributions. We are talking about sampling distribution. We're talking about, this is kind of a good data, good information. If you take all of the samples, what does it mean by sampling this? What does it mean by this? This is important. What does it mean by this? If you take all of this possible samples, right? The mean lunch for this sample from this population is going to be 49%. Or, the mean that between 12 and 13, the probability that the mean is going to be between 12 and 13 is going to be 49%, right? So this is very important, because there's no need for you to take so many samples. You can tell me some good information about that one.